Hi, folks. Welcome to Introduction to Psychology, 12th edition. James Kalat. Today we are doing a very important chapter. All the chapters are pretty important, but this one is particularly important, and especially some of these earlier ones, they build on each other. So if we don't understand, you can still get a lot of good information out of this course if you don't understand this chapter very well, but the better you understand this chapter, the better it will help you understand all the material, and also just in general, we live in a world where we are exposed to information about various scientific studies. So having some ability to understand what these studies are, how they're conducted, what we should make of various findings is definitely a very useful skill to have at this point. So hopefully by the end of this chapter, you will have a better idea of science, yay, and also how psychology is a science. Okay, let's try that. Our icebreakers. Okay, by the end of this chapter, you should be able to discuss the importance of replicable results. So replicable means when we do a study, we should be able to do that same study again and get the same results, right? There's often, when we do these psychology studies, an element of random chance to it. You're not studying everyone in the world, you're studying only a subset of those people. Maybe your study has 20 or 30 or 100 or 1,000 people in it. That's not 8 billion. So we want our study to apply to 8 billion people, or maybe all women or all men or all people from America, or whatever the case may be. Or if it doesn't apply to all, we want to know why and who it doesn't apply to and why. So we need to be able to replicate the results to be confident in them. There are essentially two things: falsifiability as well as proof, right? So proof is this kind of positive evidence for your theory. Falsifiability is trying to falsify a theory. So we'll talk about the importance of falsifiability in science. Explain why scientists seek the most parsimonious explanation of any result. Parsimonious means simple. There's something called Occam's razor, which says that if everything else is the same, then the simpler explanation is the better. In science, we look for simple explanations rather than very complex ones, right? So, and this principle originally comes from, the transition from a religious worldview to a scientific one. So, prior to the kind of modern scientific revolution, humans were doing science, but there was an element of religion mixed in with it. So it's like, okay, well, the planets rotate around the sun, and you can describe that in a mathematical law called gravity, but then there's also God, and God is the one making the planets go around, right? So Occam's razor says, well, actually gravity is what's making the planets go around. We don't need this additional layer of explanation that isn't actually telling us anything. 2.04, explain why most psychologists are skeptical of claims of extrasensory perception. Well, because we don't have good proof for it. End of the chapter, you should be able to give examples of operational definitions. That's an important concept we'll talk about. How you measure a certain concept. Distinguish between convenience samples, representative samples, random samples, cross-cultural samples. Important stuff there for understanding how science is done. We will get to that. Explain why experiments can lead to cause and effect conclusions, whereas correlations do not. So if you take nothing else away from this unit, the most important thing to take away is that correlation does not equal causation, but understanding why that is. Cite pitfalls that might compromise the effectiveness of a survey or an experiment. Okay. Objectives. Describe how researchers use descriptive and inferential statistics to evaluate the results of a study. We are not doing science if we are, number one, not collecting data, and number two, not analyzing that data using statistics. Anything that does not do those two things is not science. Sometimes scientists will write theories based on, trying to piece together existing evidence. So that might be a slightly strong claim. All science comes back to and has to be rooted in those things. Discuss reasons why a study's results might not be replicable. Discuss how psychological researchers deal with ethical issues. All right, so a lot of important, good material. Let's get right in. Evaluating evidence and thinking critically, Unit 1, Chapter 2. This is driving me crazy. Let's see if we can put this over here. Woo! Okay, let's try that. Science is carefully gaining, testing, and evaluating knowledge. So a little definition there. Is it the perfect definition? It's something good enough, I think. Research starts with careful observation and follows a sequence of steps. So you've probably heard some version of this before. The scientific method, we come up with a hypothesis. We're testing that hypothesis. We look at the results. We collect the results. We interpret the results. This has to be done using statistics. And then we try to see if the finding is real. And there's a few different ways to do that. There's kind of a little bit more to this in that we publish our results, we get feedback from the scientific community, other people interact with our work, they publish results that either supports or contradicts our work. And so it's this kind of, science is really a conversation between smart people all around the world doing experiments and sharing their results. So someone says this in their study, and then someone else says, oh, that's interesting, but what about this? And maybe they contradict it, or maybe they support it, or maybe they modify it slightly. And over time, closer and closer towards better understandings of things. Steps in an experiment. We've got our hypothesis. We've got our method to test. Our hypothesis is that people that you using your phone for a long period of time, say 2 hours, is going to make you more anxiety than when you started. Okay, what's our method to test? Well, we bring people into the lab. We have them stare at their phone for 2 hours on TikTok or whatever app we choose. Do we get results that support our hypothesis? So we measure their level of anxiety at the beginning of the session. We measure their level of anxiety at the end. We see if it supports or contradicts our hypothesis. If it supports, our confidence is enhanced. If it's the opposite, our confidence is diminished. But it's not, so maybe we think we're right, but maybe we think, you know what? It's not about one session. It's about we'll do it every day. So maybe we have people do this 2-hour thing every day for 30 days, and then we measure, right? So you might modify your hypothesis, you might discard it, or you might retest it just using a different methodology, right? Now, we don't want to just sort of torture the methodology to get the result we want and keep doing study after study after study until we finally somehow prove the thing we want to prove. But we also don't want to give up on a theory too quickly if we feel confident in it. So it's, and then say you do find the right methodology and you get a positive result after 10 negative results. Well, that's a little concerning if you're an ethical scientist. You don't want to just take this one positive result and say you've proven it. What you now need to do is say, okay, I figured out how to show this. Here's what I didn't understand about these earlier experiments. I've now modified my experiment to do it better. And now I can get this result that I think is true consistently. And if you can get to that point, maybe you're onto something. All right, replicability. Replicable results are data that anyone can attain at least approximately by following the same procedures. So in a scientific paper, a study that you publish, there'll always be a method section where you explain exactly how you conducted your experiment. So that any other research can read your method section and they should be able to do your experiment and get the same result. So that is for purposes of direct replicability. There's also something called conceptual replicability, which is essentially doing a similar experiment to replicate the same concept, but in a different way. A meta-analysis is after you have a lot of studies published on a particular topic, you can then do a meta-analysis. And what that does is it combines the results of many studies. So we will be looking at some scatter plots later in this presentation. You know, you'll have your little x-axis and your y-axis, and you'll have lots of points scattered in there. And when you conduct a study, each one of those dots is a data point. It's a participant. It tells you what their scores were on two different axes, right? Maybe social media use and depression, to use the example, right? One, maybe the y-axis is social media use, x-axis is depression, or vice versa. It doesn't really matter. Every person will have a score for social media use and a score for depression and anxiety. Okay, when we do a meta-analysis, we still end up with that same scatter plot. But instead of each dot representing an individual participant, what we have is each dot represents a study. So each dot could represent 100, 1,000, 10,000, 100,000 people. So when we do a meta-analysis, we're including often tens or hundreds of thousands of participants because of the amount of studies we're bringing into it. We get a lot of results on a certain conclusion, and then we meta-analysis. And after we have enough data to conduct a meta-analysis, then we can start to feel confident that, okay, we've got something real here. So how do we evaluate scientific theories? A theory is an explanation or model that fits many observations and makes accurate predictions. So what we're looking for is something that a theory has to make predictions, right? So say you've got your theory of evolution. Well, theory of evolution says that animals, the diversity of mammal life we see here happened after the dinosaurs went extinct. I mean, that's not the core theory of evolution, but it's one implication of the theory. Okay, so the prediction then, if we take that aspect of the theory, is that the mammal fossils should be above the dinosaur fossils in the ground because the dinosaurs died earlier. They got buried under deeper layers of sediment. And of course, that's what we find. Of course, there's many other predictions the theory of evolution would make. If I've got a theory about depression or a theory about aggression, people that have experienced relationships from their parents, right, physical abuse, they're more likely to perpetrate physical abuse on other people, or more likely to children that experience physical abuse at home, more likely to bully other kids in school, right? It has a prediction, and now I can go out and test it. I can collect data. Something is not a scientific theory if it's not falsifiable, right? So generally speaking, religious claims are not scientific theories, right? So if I say, I believe in the Big Bang happened, it's the start of the physical universe, but I believe that God created the Big Bang. Well, there's no way to prove or disprove that because all the evidence we have is within the physical universe. We have no idea what is outside the physical universe. So that's not a scientific claim, but it's not such in terms of science because science can't say anything about it. It's not falsifiable. So we have to, if we have a theory that can make predictions, what that means is we can then falsify that theory, or we can find evidence that supports it. And as scientists, we actually spend a lot of our time trying to falsify theories rather than prove them. And our best theories are ones that essentially have proven to be unfalsifiable. No one has been able to falsify them. Proof refers to an obligation to present evidence to support one's claim. So obviously any theory has to have evidence. No one's going to put forward a theory in the scientific community without any evidence. Now the question is, someone puts forward a theory, or we think of a theory ourselves. Now we have to figure out ways to theory is wrong. If we can't figure out a way to prove our theory is wrong, we publish it. We publish a paper about it. Then it goes to the scientific community to try and prove our theory wrong. If no one can prove it wrong, then it generally becomes accepted as a scientific fact. Okay, parsimony. Given a choice among explanations that seem to fit the facts, we prefer the one whose assumptions are fewer, simpler, and more consistent with other well-established theories. Degree of open-mindedness refers to willingness to consider proper evidence. I actually don't know what this image is supposed to be. I have not read this part of the textbook, apparently. So, motion machine. The point is, we have a theory. Our theory has to explain the evidence. Our theory has to not have any evidence that goes against it. Our theory has to fit with other well-established theories, right? So if you have a new theory that explains something, but says, well, actually gravity is not true. There's no such thing as gravity. You better have a lot of evidence for that if you're going to want me to throw out the theory of gravity, right? So with other well-established theories. So, our theorizing in science is very much constrained because there's all these facts, right? There's all these different theories and things we've discovered. So you're not just like making things up willy-nilly. There's a very kind of narrow range of things you can make up. And within that narrow range, we tend to try and find the simplest explanation because those ones tend to be true. Applying parsimony, extrasensory perception, the claim that some people, some of the time, acquire information without receiving any energy through any sense organs. Well, anecdotes. There are reports of isolated events which might seem impressive but are not scientific evidence. Professional psychics typically use the same types of deception as those used in magic arts. Experiments are conducted under controlled conditions, and they provide the only evidence of ESP that should be considered. So what we want to do is focus on experiments, and experiments have not really shown that people can, for example, use remote viewing or things like that. So what does it mean to conduct psychological research? Basic research seeks theoretical knowledge. Applied research is like, in psychology, it might be can we come up with a drug to reduce depression? Theoretical knowledge might be, how do people identify an animal, a cat, as a cat versus a groundhog or a dog or a squirrel? Operational definitions specify the operations or procedures used to produce or measure something, ordinarily a way to give it a numerical value. So we mentioned this kind of hypothetical experiment. We want to understand the relationship between social media use and depression. So what we now have to do, we have our two variables. One variable is social media use on the one hand. The other variable is depression on the other hand. I now have to come up with a way to measure these things, which means I have to operationally define them. So say for social media use, I want to operationally define social media use as how many hours a day or minutes a day or seconds a day a person spends on a given app. And then for the depression, I want to operationally define depression using a particular, I think there's something called the Beck Depression Inventory, I believe it's called, BDI, fairly commonly used. It's a series of, let's say, 6 or 9 questions. You ask people about how they've been feeling lately, right? So now we have operationalized these concepts. Now, I could have a more behavioral definition of depression, right? So we know that depressed people have trouble sleeping. We know that depressed people tend to isolate. Maybe they're less active. They have negative thoughts about themselves, right? So I could choose to try and measure depression using some sort of behavioral measurements, like how many times do you go out of your house to do something fun per week? Or I might operationalize depression based on some sort of brain scan. Now, we don't really have good brain scans for depression, as far as I know off the top of my head, so that might be trickier. We can measure cortisol fairly well, so maybe we want to say that cortisol levels are going to be a proxy for depression, and we're going to measure depression that way. So these are really key choices, and your theory could be correct, but if you don't operationalize things in the correct way, then you may not get the result you're looking for. So say you do a study, you don't get the result you want. One important question to ask yourself is, did I operationalize my variables properly? Talked about applied research, sampling, a group of people being studied, behaving unusually in some way. Look, sampling is just taking it's a slightly confusing definition. Sampling is when we take some subset of the population. I want to run my study. It's supposed to be about people. I can't study 8 billion people. I'm going to recruit 50 random people from the internet. That's my sample. Will it be biased? Maybe. If I recruit 500, depending on how I recruit them, it will be less biased. So we can go out of our way to say, I want, the same percentage of Black people and white people as there are in the population of the United States. So there's different ways we can do that, making sure we have roughly even numbers of genders or corresponding identities, religious identities, whatnot. But sampling is essentially taking some smaller group from the population. Behavior of the participants involves research participants behaving differently because they're generally being observed. So that's always a question, a concern when we're doing research. You bring someone into the lab, you ask them how depressed they are. Are they going to exaggerate how depressed they are? More likely they might hide how depressed they are. Just the fact that they've come into the lab, they're in a strange setting, they're surrounded by strangers, now they're feeling more anxious than they would normally. So we have to always be aware of, in what ways might the fact that they are participating in a study be affecting their behavior, and try and account for that in the way we conduct our studies. Okay, let's talk about the difference between a convenience sample and a population sample, a representative sample. Convenient sample is anyone who's available can be chosen, creating the ease of study. Samples are easy. I would say easier to get. It's never easy to get people. It's always a challenge when doing science. And a result, this method may be overused. Results may not be generalized to the whole population. Same percentage of male, female, white, black as the whole population or demographic category. Results similar to whole population demographic categories. Sample may be representative in some ways, but not others. So basically, when we go out of our way to try and get a sample that looks like the population we're trying to study. If you're trying to do a study about trauma, you probably don't want a sample of all, kids whose parents are millionaires. There's going to be a lot less trauma in that group. They're not going to be representative of, kids who are from rural Appalachia or inner city Chicago. Random sample, everyone in the population has an equal chance of being chosen. I mean, that's essentially impossible. There's no way to pick to have a study where the population is the entire United States or all people in the world, but that's what it would be. So really, it should say impossible to attain. Example is when we choose people from different cultures. Of course, probably no studies have people from every single culture. So, a lot of times we're just doing, America and Japan or China and Korea or something like that. Population. All right, we're skipping those. Blah, blah. All right. So those is when we're doing an experiment. We're picking people to do an experiment on those people. Another way to do research is observational research designs, where we just observe people. This can happen in a naturalistic setting. Maybe you go to a college campus and sit on the green and you observe people, and you just, you want to note down the size of the groups that people are sitting in and maybe compare men and women in the different sizes of groups or something like that. Is a detailed description of one particular individual. Neither of these are considered observation can be scientific if you're recording data in a particular way. Case history is not, but it can lead to experiments and can have value in other ways. Survey is a study of the prevalence of certain beliefs, attitudes, or behaviors based on people's responses to specific questions. Getting a random or representative sample is especially important with surveys. The seriousness of those being interviewed and the wording of the question affects survey results. The wording of the questions is absolutely huge. If you get a certain result that you weren't expecting, you should probably questions in a slightly different way, because minor changes in the way questions are worded can have big effects in the way people respond. Involve wording questions of a survey to encourage the answers they hope to receive. So obviously, as when researchers do research, they tend to word questions in ways that support their conclusion. We want to kind of fight against that tendency. But people don't always do a good job of that. And that's where it's up to the rest of the scientific community to come in and say, hey, you did this research, but the way you asked the question was really kind of leading and biased. And we reran your study and we asked them the same question, but we just asked it in a slightly different way and got a very different answer. Okay, here is an example, a little hard to read. Let's zoom in a little bit. Okay, so here we have 70% opposing, 5 don't know, 24 supporting. And here's how it's phrased. Stem cells are the basic cells which all of a person's tissues and organs develop. Congress is considering whether to provide federal funding for experiments using stem cells from human embryos. The live embryos would be destroyed in their first week of development to obtain these cells. Do you support or oppose using your federal tax dollars for such experiments? Okay, so you get a large majority opposing. Here on this side says sometimes fertility clinics produce extra fertilized eggs, also known as embryos, that are not implanted in a woman's womb. These extra embryos are either discarded or couples can donate them for use in medical research called stem cell research. Some people support stem cell research, saying it's an important way to find treatments for many diseases. Other people oppose stem cell research, saying it's wrong to use any human embryos for research purposes. What about you? Do you support or oppose stem cell research? So here you have almost an opposite result. Here you have almost 60%, over here it was 70s. But here it's opposed. Now, what we did was just change the wording. I think we obviously gave more information. but it gives you a sense of another classic study. So these are called framing effects. Another classic study is if you're selling meat in the supermarket and you say 10% fat versus 90% lean, people are like, ooh, 90% lean, sounds great. If you write 10% fat on the ground beef, people are gonna be like, sounds kind of gross. Okay, so here we get to some of those dots that we were talking about earlier, and we're now going to be talking about correlation. Let's go out a little bit more. So over here we have a little chart, and this would be so we have our two variables. Sorry, I don't have a better way to do this. Just got to move this thing around. All right, so we have our variables, fish consumption, and it says pounds per year. That is our x-axis. Here's our y-axis. This says major depression annual prevalence. So this is rate per 100 people. So this spot up here is West Germany. So 5 out of 100 people in any given year have depression in Germany. This spot on this graph also records their fish consumption per year in pounds, right? So Germany is the lowest on the chart. We have to go down here. Looks like they eat somewhat less than 30 pounds of fish per year, right? So maybe 28 pounds, let's say. New Zealand, they consume 40 pounds of fish, and they have a slightly higher rate of depression, almost 6. Canada, about 50 pounds of fish, maybe a little higher, about 5.2 or something. France, Puerto Rico, okay. Puerto Ricans are consuming about 70 pounds of fish per year. Similar level of depression to the United States, 3 people per 100, but less fish. Taiwan, dramatically less depression, 1 per 100, more fish. Korea, more fish. We're looking at about 110 pounds of fish, 2.5 people depressed there. And Japan, almost 0 people reporting depression, and they're consuming about 140 pounds of fish per year. Okay, so this line here is called a line of best fit. So when the line is sloping down like this, that would be a negative correlation, meaning as one variable goes up, right, as we move further along this x-axis, the values on the y-axis are decreasing, right? So high on x, but low on y. High on y, low on x, right? So that'd be a negative correlation. You could also have a positive correlation would be a line going this way. As x increases, y increases, and opposite. And if there's no correlation, that line would just be going straight across the middle or just slightly tilted. The coefficient here is this r. It's a 0.84. That's quite a high correlation. Well, a negative 0.84. And the p-value refers to how likely this is due to chance. That's a low p-value, so it's unlikely that this correlation has to do with something else, right? So this correlation does not prove that eating fish reduces depression. This is just a correlation. Correlation does not equal causation, but to see a correlation, we should probably try and figure out what is going on here. Is there a causal relationship? How can we test whether there's a causal relationship? So if we call these two variables x and y, there's always 3 possibilities. With the correlation is that x is causing y, right? Living in one of these countries is causing people to eat more fish, right? So maybe island countries, we see that there's consumption in island countries. Living in these countries is causing less depression. Maybe it's the fish eating is causing the living in the countries, or maybe it's a third variable causing both of them, right? So x could be causing y could be causing x, or some third, fourth, fifth, sixth variable, we'll just call them all z, could be causing both x and y. Here are some different scatter plots. We've got our things represented on the x and y axis. You can kind of see here that this is like a positive correlation. If you were to draw a line through this data, it would look like it's going upward, a kind of upward diagonal line. Here, this is not perfect data, but there's going to be some sort of a downward negative correlation. The line's going to look something like this. So when you draw the line, there's a mathematical formula, and the way the line works is they draw the line such that half the dots are below it. Now that's not exactly the right way. That's above it. The distance to the line is the same when you add them all together as the dots below it. This one is just going to end up being a straight line going across, probably somewhere up here, right? So that's a no correlation. Okay. So what you see here is this y-axis is measuring final exam score. And we've got 3 different x-axis. So first test score. So there's a positive correlation between our first test score and our final exam score, right? So people that were smart and good at school testing at the beginning of the semester, they were good by the end of the semester. That is a pretty typical finding. Intelligence is a stable trait. Absences. People that had more absences tended to do worse on the final exam. That makes sense. And here, last 3 digits of social security number. This should not be correlated. There should not be a relationship. And as predicted, there is no correlation in that one. It would have been helpful if they would have drawn the line, but illusory correlation is an apparent relationship based on casual observations of unrelated or weakly related events. It may be caused by a placebo. Correlation does not equal causation. Correlation indicates associated with each other. Okay, so let's call this our X, depressed mood. Sleep is our Y. So does X cause Y? Does a depressed mood cause impaired sleep? Or does the causation go in the other direction? Does impaired sleep cause Y? So in this first example, X causes Y. Here, that arrow is pointing in the opposite direction, is that Y causes X. Or maybe family conflict or just some other stressor is causing both depression and the impaired sleep, right? So it also could be that family conflicts, these can get more complicated when we diagram these causal relationships, because it could be that family conflicts cause X, depressed mood, family conflicts cause Y. It could be that they cause both of them, but then you could also have a situation where the family conflict causes the depression, but then the depression causes the impaired sleep. So now we need another arrow going from X and Y. But then once our sleep is impaired, it could be that that goes back the other direction and increases depression, right? So we've got this sort of feedback loop where depression is causing sleep problems and sleep problems are making the depression worse, which is making the sleep problems worse. And then guess what? If the depression's getting worse and the sleep problems are getting worse, that could cause more family conflict, which could cause more depression and more impaired sleep. It's a big doom circle loop thing. Okay. Whew. Calm down. Calm down. Relationships can be complicated, and these causal arrows can go in multiple directions, back and forth and back. So in actual papers that are published on this stuff, you can see causal diagrams that take up whole pages of 20 different variables with arrows going in all different directions. Now, we wouldn't just make stuff up. We don't just like drawing fancy diagrams with arrows pointing here and there. What you'd also see is R values and P values going on each arrow to show you which relationships are statistically significant and which are not. Okay, let's move on. Need a drink of water first. We are on slide 30 of 47. Hang in there. An experiment is a study in which the investigator manipulates at least one variable while measuring the other one. So an experiment always has an independent variable and a dependent variable. The independent variable is the variable that the experimenter changes or controls. The dependent variable is the item the experimenter measures to determine the outcome. So if we're doing an experiment on social media use and depression, which is the one we're going to measure, which is the one we're going to manipulate. Presumably, we're going to be measuring depression and we're going to be manipulating social media use. We're going to tell people, use social media use for this amount of time, for this time period, for this length, use this type of social media versus that type, et cetera, et cetera. These are so named because if our theory is correct, the value of the dependent variable is value of this variable is dependent on the independent variable. It should be affected by it. Okay, more terminology. An experimental group, a group that receives the treatment that an experiment is designed to test. So say we want to know, say we believe that using TikTok is worse or say YouTube Shorts or TikTok, whatever, is worse than watching long form YouTube videos. So the control group is going to be the group of people watching long form YouTube videos. The experimental group is going to be people watching YouTube Shorts. Or maybe we have a different control group, and the control group is reading, and then the experimental group is YouTube Shorts, and another control, which is YouTube long form, right? So it's just the control group is supposed to be a neutral condition. In medical studies, it's typically like a placebo or sugar pill. The experimental group is the group that's being experimented on. They're getting the treatment, whatever that might be. So in medicine, it's a drug. In psychology, it's some sort of manipulation. Maybe we're subconsciously exposing them to the word death, or maybe we're making them remember something, or maybe we're stressing them out and asking them to do a task while they're stressed out, things like that. Random assignment. This just means that people don't get to choose what group they're in. They're randomly assigned to be in either the control group or the experimental group. Experimenter bias in blind studies. So experimenter bias is the tendency of an observer, usually unintentionally, to misperceive the results. So for someone who reports data without knowing the researcher's predictions, a single blind study is a procedure in which either the observer or the participants are unaware of which participants received the treatment. And a double-blind study, research in which both the observer and the participants are unaware of which participants received the treatment. Okay, so typically what we want is, when we're doing a study, we want it to be double-blind. So we have a control group. The participants don't know who's in the control group. The participants don't know who's in the experimenters, that's why it's double-blind, also don't know who's in the control group or the experimental group. Our sample is random as much as possible. Control all the sort of factors that might unduly influence our experiments so that we can properly test it. And be confident in the results. Demand characteristics. These are clues that tell participants what is expected of them and what the experimenter hopes to find. We have, so typically you have a person, who's conducting the experiment, overseeing the experiment. They know what's going on. They would have a research assistant who doesn't really know what the experiment's about, conducting these experiments. And hopefully that reduces demand characteristics. But it's probably, there's always the ability that can happen. Okay, problems with a before and after study. Before and after study often leads to results that are hard to interpret. It is better to compare results for different groups, right? So say you want to test the antidepressant. You could have the same people not take the antidepressant for a month and then take it for a month and see what happens. Or you could have two different groups of people. One group takes the antidepressant for a month, one group doesn't, and then you compare them. Generally speaking, now, and then sometimes you can go back. You can be like antidepressant, no antidepressant, antidepressant, no antidepressant. You can have a participant go through these different cycles. There are advantages and disadvantages to doing it both ways. Now we get to the fun stuff. Statistics. Statistics. Yes, it is math, but it's not boring. It's interesting. It's exciting. If you don't have a basic understanding of statistics, it's very hard to sort of understand the modern world we live in. So it's a good idea to take a stats class and learn some stuff about it. We won't be doing enough in this class for you to really learn a whole lot about it, but the more you know, the better. Knowledge is power. Okay, this descriptive statistics is a mathematical summary of the results. So we have a data set, right? We have a list of measurements of something, right? Could just be rocks and how much they weigh, whatever. We've got a data set. Descriptive statistics essentially just describe the objects in our data set using whatever we're interested in: height, weight, income, education level, things like that. So the kind of basic things in terms of statistics are all ways of measuring the central score or central tendency, as it's usually called, and those are the mean, the median, and the mode. Now, typically, we are most interested in the mean. That's the most common usage. Median would be second common. mode not used that commonly because it can very much be misleading. So say we look at this people. We've got one person making 76,000 a year, one person making 15. Why is it organized like this? I don't quite understand that. Okay, one person making 10,000, two people 10, one 5,700, three people 5,000, four people 37. Oh, okay, I see it's going from low to top. Never mind. Duh. Okay, mode. So the most common is 2,000, but that's the lowest. The median, this is the one in the middle. So that means there are however many people down here. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. So there's 12 below, 12 above. That makes this guy the median. The mean is we average everyone's income, divide it by the total number, which should be 25, if my counting was correct. And that's the number we should get. So what you can see is, because in this data set, it's not normally distributed. So normally distributed data set, most people would be here in the middle. This is a data set that is skewed. We've got our mode at our lowest value. So when our data set is skewed, this mean and median don't actually tell us a whole lot about what's going on in our data set. So if our data set is the mean and the median will be fairly we usually use the mean for these things. But so we should know what these are. We should know when they're useful, what they say, what they don't say. A politician, I could say, look, the most common income in, our village is $2,000, and this is crazy. And that would be true, right? Someone else could say, look, the average is 5,000, but actually mostly it's 2,000, and really the average is only 5,000 because of like 4 people who are making 10,000 and above, etc. So sometimes these are very useful. Sometimes they hide more than they tell. We have to sort of know how to interpret them. Okay, there is another aspect to descriptive statistics that is called standard deviation. It refers to how widely dispersed our data is. But since it's not on the slides, we will ignore it for now. Inferential statistics. These are statements about a large population based on inference from a small sample. Certain kinds of statistical tests determine the probability that purely chance variation would achieve a difference as large as the one observed. The result is summarized by a p-value, p as in probability. The smaller the p-value, the more impressive the results. Okay, so the heights of 10 men and 10 women. And, just so happens that the men are, in a given college class. There's 20 people, 10 men, 10 women. I take their heights. Now, turns out that the women are on average taller. Well, this is an average, the men are just random students at Hawken College. But I also but the women in the class, the girls in the class are all on the basketball team. So, they are all 5'8" and above. So I want to know, okay, so I've got a mean height for all the men and all the women in this class. Are women on average taller than men, or is there something going on here? There are statistical procedures I can use to tell me whether this is probably due to chance or whether this is actually probably true, a true result that will hold in the population. So if I were to run a test like that and I only had 10 in each group, I would get a high p-value, which would mean a low probability that my hypothesis is true. If p is less than 0.05, researchers generally consider the results statistically significant or statistically reliable. Statistically significant, statistically reliable results that chance alone would be unlikely to produce. Statistical significance depends on 3 factors: the size of the difference between the groups, the number of research participants in the group, and the amount of variation among individuals in a group. As I mentioned, this is all important stuff. There's no way for me to explain it to you in 2 minutes, and you can learn it, but steps are worth knowing. I think the most important thing here to understand is this term statistically significant can be slightly misleading. So say I give 10,000 people an antidepressant. and there's a statistically significant difference after 3 months. People taking the antidepressant have a lowered level of depression. That level is statistically significant. Now, if I have 100,000 people in that study, even a minor difference on an average score of 5.3 to 5.1 is going to be statistically significant. Now, that doesn't mean that it's clinically significant. It doesn't mean that on average, it doesn't mean that every person feels less depressed. It could mean that some people feel a lot less depressed and some people don't feel less depressed at all. It could mean that everyone feels a teeny tiny bit less depressed in their answers, but it doesn't actually make a meaningful difference in their life, right? So there's a difference between statistically significant and clinically significant. And then there is a big difference between something being statistically significant for an entire population versus it working for every single person within that population. Okay. A growing trend for research is to show the means and the 95% confidence intervals for each group. 95% confidence interval, the range within which the true mean lies with 95% certainty. So this mean in these examples, this little bar here, this little eye kind of thing, what this is showing is there's a 95% chance that the mean, this was our actual observed mean, the top of this bar, the true mean lies somewhere in this range, right? So you can think about your weight. Say you weigh yourself every day. Some mornings it's 151, some mornings it's 153, some mornings it's 155. So really your weight, there is a mean for your weight, which is the average of all your scores, but your real weight is kind of whatever, it's in that 5 pound kind of fluctuating window or 4 pound or 3 pound window. That's kind of sort of like this 95% confidence interval. It's not a perfect example, but it's something like that. So it can be more useful because here when we look at this data, we see a much wider range. This is because just the way the data looks without getting into the details. So sometimes this 95% confidence interval will be actually fairly close to the mean, but here there's a pretty wide difference, and that's worth noting. Replicability issues, because researchers generally publish only the results that look impressive. An unknown number of reported results may have arisen by accident. Say you do 10 studies, 9 fail, 1 is a success, you publish the 1. Well, those 9 studies are not irrelevant. They do tell us something. It's just they never got published. Sometimes that's called the file drawer problem. Psychologists are becoming more interested in trying to replicate results. Harking is called hypothesizing after results are known, pretending you predicted something when results are already known. So you have a hypothesis, you collect data. Technically, you're not supposed to use that data for anything other than your original hypothesis. Also sometimes called p-hacking or data mining. Otherwise, you're just digging through data trying to find a random connection. And if you start looking for random connections, you can probably find some. P-hacking is analyzing the data one way after another to find a way that is statistically significant. Explaining the problems of these probably goes beyond the scope of this course, but just generally know that we're supposed to have a hypothesis and use our data only to test that hypothesis. If we do find a connection in our data by p-hacking or harking, what you then want to do is do a whole bunch more experiments to try and prove that connection. Okay, moving on. Ethical considerations in research, and we are in the home stretch, folks. In humans, all experiments need to be pre-approved by an institutional review board. So at Ohio University, for example, or any university, they have to submit their proposals for research to an IR review board. These are people who are general community members, and they kind of oversee the research. They approve it, form consent for participants. Must minimize the risk to participants. Sometimes deception is allowed, but only when necessary. And the risk to participants must not be greater than in everyday life, right? So to get to an experiment, you have to walk up some stairs in the psychology building. Well, that risk is not more than your normal day of walking upstairs to your dorm or your other class, right? So the risks should not be anything more than normal life. In non-humans, basic processes such as brain mechanisms, sensation, hunger, and learning can be studied. Control of aspects of life that people will not let them control. So these are some reasons why we would do research in non-human animals. We can study behavior over an extended period of time. We can study a rat who doesn't live that long over the course of its entire lifetime. Animal research is somewhat controversial because of ethical issues, and it still must also face a review board. Okay, summary of our results. Move this over here. Now the lesson has ended. You should have learned how to discuss the importance of replicable results, contract falsifiability with the burden of proof, explain why scientists seek the most parsimonious explanation for any result, explain why most psychologists are skeptical of claims of extrasensory perception, give examples of operational definitions, distinguish between convenience samples, representative samples, random samples, and cross-cultural samples, explain why experiments can lead to cause and effect conclusions, whereas correlational studies do not, cite pitfalls that might compromise the effectiveness of a survey on an experiment. And lastly, describe how researchers use descriptive inferential statistics to evaluate the results of a study. Discuss reasons why a study's results might not be replicable. Discuss how psychological researchers deal with ethical issues. Okay. I'm tired. You're probably tired. You made it to the end. Congrats. That's a lot. Take your time going through the chapter, reading it. Feel free to explore the internets, the YouTubes, to learn more. For example, you could always Google correlation does not equal causation and see what comes up. You could learn about sampling. You could sort of do more on your own to learn about this stuff because it may take you a little while to grasp these concepts. So good luck with that. I will talk to you all at our weekly meeting.